This tutorial is going to talk about ATP, and we're going to talk about ATP as an energy source, and how we can utilize coupling ATP hydrolysis or ATP phosphoryl group transfer to other enzyme reactions to make endothermic reactions overall exothermic. So ATP is by far and away the most important form of chemical energy that we have in the cell. And every day you use an amount of ATP equivalent to your body mass. So as an aside here, I would say go ahead and sit down and calculate the number of moles of ATP used by a 150-pound person per day. Now the hydrolysis of ATP is sufficient, like I said, to convert these non-spontaneous reactions into overall spontaneous reactions. And we can illustrate that with a simple example here of glucose 6-phosphate. So, like we say here, consider the reaction of glucose in the pyranose form with phosphoric acid. And in this form here, HPO4 2-, which is the form that it's going to be at physiological pH, right? Phosphoric acid has 3 pKa's, one about 2, one about 7 or so, one at about 12. And if we want to get glucose to react with HPO4 2- to generate glucose 6-phosphate, then the overall reaction that we're talking about is here. But we're really unable to write a reasonable mechanism for this reaction. And that's because we're talking about a nucleophilic type reaction here where the C6 hydroxyl of glucose would have to be the nucleophile, and that's a pretty weak nucleophile. And phosphoric acid in this form is not a very good electrophile because we've got localized negative charge around that phosphate. The phosphate is going to be electron deficient, but getting a nucleophile through that electron, or that negative electrical charge is going to be an issue. So how do we deal with this? Well, we need to think about breaking this down into separate half reactions here. Again, this is something you talked about in Gen Chem 2, and we want to bring it back to the surface. So reacting glucose with HPO4 2- to give you glucose 6 phosphate and water has the problems that we talked about, but it's also an endothermic reaction. So we need a little more than 3 kcals per mole of energy to be able to make this happen. So it's not a spontaneous reaction to begin with. Now, if we take our ATP and hydrolyze it to form ADP and our HPO4 2-, this is a very exothermic reaction. It releases a whole bunch of energy. Okay. Now I've got grayed out here this reverse reaction of this. If we take this reaction and flip it on its head, and we try to combine ADP with phosphoric, this dianion of phosphoric acid, then we get ATP and water. This takes the exact opposite amount of energy here. So here we get a release of 7 kcals per mole of energy. Here it requires that much. And if we try to go ahead and add these reactions, we don't get the total reaction that we're interested down here. If we add this reaction, then the water cancels on both sides, the HPO4 2- cancels on both sides, and we get this net equation that we're looking for. So it's only when we have the half reactions in the right orientation can we add together add the reactions, get the overall net reaction that we're looking for, and we get the total energy. So here we have to add 3.3 and minus 7.3 kcals per mole. We get minus 4 kcals per mole. So we take this endothermic reaction and convert it into an overall exothermic reaction when we couple these reactions. Now keep in mind that the half reactions don't occur by themselves. This is just a way of understanding the energetics that's going on here. So what we're talking about in all actuality is glucose reacting directly with ATP in an enzyme active site to transfer the gamma phosphate group to glucose in this case, and generating ADP. Okay, so you should be able to sit down and scratch out a mechanism for this, and there are a couple of issues here, right? We've talked about some of the problems, and we've also talked about in various problem sets and such how we could rectify that. So you should have an idea, not necessarily about the intimate details, but at least have an idea about the steps that should have to go into this. So again, kind of to reiterate what I just mentioned here, that this reaction is thought of driving the formation of glucose 6-phosphate via ATP hydrolysis. But again, these half reactions don't occur individually. Instead, there's a direct attack of the C6 hydroxyl glucose on the gamma phosphate, specifically the phosphorus atom of ATP, and then ADP is the leaving group. And you should be able to rationalize at this point too why ADP is a good leaving group. Right? We can delocalize that negative charge that's generated. So the question here is how many electrophilic positions are present in a molecule of ATP, and write mechanisms for the reactions of ATP with a general nucleophile, just NU dot, a lone pair here. And what is the leaving group in each case? And what has to happen to be able to allow that nucleophile-electrophile reaction to happen? Okay, so there are numerous examples of phosphoryl transfer reactions. In all these cases, or many of these cases, ATP is the phosphoryl donating group. And we have 3 different phosphorus atoms that are comprised in the phosphate groups here. So we got an alpha phosphorus atom, which is the phosphorus in the phosphate group closest to the ring here, beta and gamma. Okay, and you can react those with things like carboxylate nucleophiles to form mixed anhydrides. So some questions here: what contributes to the electrophilicity of the phosphates? So why is this a good electrophile, this atom? And in this form, why is that troublesome, and how do we get around it? And we've talked about why carboxylate is a nucleophile rather than an electrophile like carboxylic acid is. But if you're going to have a reaction between a carboxylate and the alpha phosphorus, the beta phosphorus, the gamma phosphorus, what are the products in each case? And then what kinds of things decide the leaving group? You need to be able to stabilize each of those leaving groups. And keep in mind that these reactions are occurring in an enzyme active site. Okay?